Let's look at the representation more closely. This slide, first of all, shows the essential interconnection between the ACS and the NACS, which we'll get into later here. As you can see, there is a top level and a bottom level in both, and that there is a bidirectional flow, if you will, between the top and bottom levels in each, along with communication across the boundaries between the NACS and the ACS. Now, the NACS is essentially a slave system to the ACS. The NACS doesn't do anything unless instructed to do so by an ACS action. And these will be something that will be the flow that triggers operations in the NACS later on. NACS then returns the result of its retrievals back to the ACS, which then aids it in making a decision as to what action to make in the world. That may not make a lot of sense just yet, but I hope it will make sense here. I put the term main movement here just as a tip of the hat to people who build video games, but basically this is an ongoing cycle that runs continuously. It is always going on here. Essentially what the ACS is doing is observing the current state, and then in the bottom level it is actually impressing the activations of what it's sensing in the world, along with other things like its state of working memory and so forth, and causing the neural nets to respond to that, and in so doing create action recommendations, which are the output nodes of the neural nets. It's also doing this in parallel at the top level, looking for rules that are potentially activatable from the sense data and working memory and goal information that it's got, and making a decision that way. And then, of course, it can then make a decision by deciding whether to choose the top level, choose the bottom level, or somehow make a stochastic decision between the two, and from that, and make that go on. And then, of course, issue the action recommendation that issues from that, see what results it has in the world, receive feedback from the world, which can then, of course, trigger learning by changing the weights in the neural nets and possibly altering how the rules are being defined in the top level. And these go on, again, bottom and top levels in parallel, if you will. Then you go back to the top, sense the world again, and keep going. It's a continuously operating loop that the ACS is always running. Now, of course, the bottom level are built with neural nets, and this is a thing where one of the points about previous implementations is that you don't really know what any individual neuron means. This is less accessible, as we say. Just as you don't know what the individual neurons in your brain signify, you don't know them here either. There's no symbolic representation that the neural net is carrying along. That's the notion that this information is inaccessible in a way you can, say, reason over or observe. The basic technique used in Clarion is a backpropagation network, a layer of input nodes, a hidden layer, and a layer of output nodes, and various ways of training that neural net. In the implementation, there's actually an abstract class for networks. You can build any network you like if you don't happen to like backprop for a particular purpose. And as I mentioned also, you can have as many specialized neural nets within the collection inside of the ACS, again, to suit the domain you're trying to model here. The information that shows up at the bottom level basically are three kinds. There's going to be the sense data. That's going to be what Clarion is perceiving in the world, and that's the entirety of what it's perceiving in the world, essentially featurized, if you will. There are working memory items, and the ACS is aware of what it's got in its working memory, and there's a current goal that it's trying to pursue, and that's going to issue from the MS in some other way. But these are three things that are representable as inputs to the bottom level. Now, one of the key ideas that comes up, especially when you get into the implementation stuff, but it's there theoretically, is we represent information as dimension value pairs. Now, a dimension can be something like color. Color can be, say, red, yellow, green, blue. Now, we do this in a way where you don't really get to represent floating point or integer values directly, because in the bottom layer, in the bottom level, if you activate a given dimension value, you're activating a particular node. So if, for example, I have some perceptual study that involves shapes and colors on sizes on screen, and I have the notion of small, red, square, then I have shape, square, color, red, size, small. I don't get to say size 13.7 centimeters or something like that, because it's featurized. We have to do it by featurizing it, which means we don't get to represent continuous values directly. Now, why is that important? Well, it kind of forces you to think about the scope of the problem or the nature of the problem you're trying to solve. One of the things I'm on now is working on building a musical agent, a musical, cognitively competent musical performance agent on a project that was example, representing the loudness of performance, we're going to use the notation from traditional music. Tacit, meaning you're not making any sound at all, but then, pianissimo with PPP through mezzo and then all the way to, fortissimo, FFF. So 10 scales of loudness. We're not saying, 13.8 decibels or anything like that. We're going straight to a more say, packetized kind of way of representing the state of the world. We do this because it's one for one. If I'm representing loudness, I need 10 neurons going into the input if I want to model 10 loudness levels. And that would be how we approach the modeling. This is very different from writing an AI thing where you might just read a value in directly and do some calculations on it. We don't really go at it that way, and that's kind of a key idea. So dimension value pairs, that notion permeates all the way through Clarion. You'll find this everywhere because, again, a given dimension value pair, when activated, means that node is turned on or given its activation level of 1. The nodes will not be activated. And we keep that idea in mind as we go forward. Again, there are three kinds of things. I think I did that slide already. DV pairs, or dimension value pairs, are then aggregated into what we call chunks. A chunk is a collection of dimension value pairs, and chunks can also be given names. In the simulation code you write, you can actually create DV pairs and chunks to hold them any way you like, and of course, because you can label them, they have external meaning when you look at log files, for example. Internally, Clarion doesn't really care what you label things, it's just going to do its thing. But the dimension value labeling is for our benefit, and the chunk labeling is for our benefit. And that's basically how that goes. This is the thing you're going to see repeated throughout all the Clarion work in the next couple of weeks as well. Don't need to get into the math too much, so I'm going to stop that. We'll go by that, and then we can mention this math either here. I do want to point out that, of course, if several nodes activate with different levels of activation, we can just simply take a winner-takes-all attitude, find the strongest activation, or apply a distribution called the Boltzmann distribution, where the chance of it being selected is a function of how activated it is. But, if you have, say, 0.7 and 0.6, the 0.7 will have slightly more chance of being selected than 0.6. That would be a way of getting stochastic behavior in there. These become tunable parameters that, of course, can also then be tweaked by the ACS later, the MCS, the metacognitive system, if you so choose. Again, all these things are simply available to you, not necessarily things you have to go with. Internally, the layout is something like this. As I mentioned before, there are three kinds of sense data things that ACS is dealing with. Is what it's sensing in the world, and that's going to be the external action network. There's going to be what it has in working memory, handled by the working memory action network, and of course goal states are dealt with in the GS action network. These are therefore connected up to other components in Clarion, like the goal state, the goal list, and also things like the contents of working memory. Am I going too fast, too slow? Okay. So questions about this so far? Okay, no questions? I guess I'm covering everything, that's great. Top level representation. Of course, the notion here is that we're dealing with symbolically expressible rules and so forth. These are, quote, quote, accessible. We can identify what it is the rule is telling us. And this is where we think of traditional consciousness as residing, if you will. This is the approach taken by, say, SOAR, which is a pure rule-based environment, which has become less so in recent implementations of SOAR. But the earlier SOAR and SCRIPS kinds of systems do that. This is a slower system than the bottom level, because the bottom level is pure neurons, if you will. This thing may involve a longer time frame in which to come up with reasoned things here. And we model this by basically producing chunk collections in the system. We have a condition chunk, which contains all the dimension value pairs saying, when you see these in the world, or in working memory, or in your goal state, then do this. The condition chunk is essentially those things you need to match in order to say this rule is activated, and then the action chunk contained in that rule is what is then exposed to external selection. Now, it may not actually get selected because, again, it competes with the bottom level on the selection process. But when a rule is activated, it does so because the terms of the rule were seen in the world and in the working memory in the goal state, and then an action was recommended for it. Now, rules come and go. I mean, as the rule extraction and refinement process works in Clarion, rules can get more specialized, more generalized, dropped all together, and so forth. And in this way, the agent does its top-level learning. Of course, at the same time, the bottom level is changing its neural net weights in terms of the connections, and it's doing that as well. These are both essentially, you can think about it, parallel systems here. Other things can be put in there too. Two other families of rules besides RER are the IRL rules, which are basically a way for you to say, here's a bunch of rules that might work. You can pre-stuff it in the box, if you will. And then a rule may get selected that way and then tried in the world. If it fails, the rule may then get dropped or reduced in strength. If it succeeds, it may become then part of its working rule set. And fixed rules are a way of basically letting you put in what we would call maybe reflexive behavior, or things that are so well learned you don't want to bother training an agent to do it. You just want to bake it into the system. So fixed rules are available there, kind of as a shortcut. But basically, you're all dealing with rule-based mechanisms at this level here. Again, a top-level rule is a condition chunk containing all the things that need to be present for the rule to be activated. And of course, this chunk may have as many DB pairs in it as you need to model the scope of the rule. And then that leads to essentially an action chunk, which is what you want the agent to do if that rule in fact fires. Does that make sense so far what that's trying to do? This is more of a symbolic kind of thing here. Now, there are other things in play here, like base level activation and so forth. A rule that was activated recently that succeeded will tend to be more likely to get selected going forward because its base level activation is higher. Over time, base level activations asymptotically go down to 0, so that rules that haven't fired in a while may not be the one most likely to get selected if there are other rules that have higher BLAs. You can also put in utility metrics and other numerical measures so that you can get the behavior you want out of how the ACS is going to behave. Again, BLA is a long tradition in CogSci, and there's the equation for it. We're not going to say anything more about it. Again, you can also build utility metrics as well and do it that way. So that's how the top level in a nutshell works with Clarion, the notion that you have essentially a rule-based system where the rules are dynamic. They can come and go and get modified as the agent successfully operates in the world. So any questions about that? Okay. Learning in the ACS, how does that happen? Well, I kind of touched on it earlier. Again, at the bottom level, we're dealing with neural nets, and the key algorithms provided in Clarion are Q-learning, simplified Q-learning, and supervised learning via a standard backpropagation algorithm. The top level uses the systems I mentioned before, the so-called rule extraction and refinement, independent rule learning, and fixed rules. So how does the bottom level work? Well, standard backprop consists of getting an error signal and then causing that to alter the weights, connecting up the nodes from the hidden layer to the output and the input to the hidden layer. And again, there's the math for it. Q-learning is a reinforcement learning method and operates a bit differently, again using an error signal to alter the weights in the neural net. And simplified is basically Q-learning but without the temporality in there too. Again, that's more detail than we want to get into today. How to work it? Well, one way, of course, the agent can learn is that it has sense data, which then leads to action chunks being issued by the agent, which then have an effect in the world. And then by noticing whether it had success with that action in the world or not, it can learn. So there's a sensory input to action loop here, where actions in the world create state changes in the world, which then lead to, are determined to be successful or fail. And then that, of course, is going to modify the agent's behavior. There's a more roundabout pathway that will become more evident later on, where sense data may also trigger changes to the goal levels, the goals that the agent is pursuing, and also how the MCS is going to alter the agent's behavior that way. Again, it uses a reinforcement signal to make the change, but it's through a roundabout pathway. And there are other loops besides that. The most direct one is simply agent does something and it succeeds or fails. It can do that if, for example, you have nothing more than an ACS in a simple agent, a purely reactive agent. But if you don't have that and have a more complicated model, you have other ways that learning is taking place inside the Clarion agent.
Let me just restate that. The two basic different ways is that you can have sensory information leads to an action, then reinforcement signals received from outside the system. You know, it would be like a tutor or something, you know, telling you, yes, you did this correctly, or no, you didn't do this correctly. The other way is this circuitous way with the MCS, where the MCS can do much more subtle monitoring, like looking at a end state for a goal and seeing how close the current state is from the end state and giving a reinforcement signal based off of the proximity to the goal state, or providing positive feedback for something which diminishes the deficit of a drive. So you can use that kind of internal type reinforcement signal generation as another way of doing that if you want to have the more kind of internalized circuitous route within Clarion.
Okay, I hope they got on the mic okay, because that is a shotgun microphone. I hope you're not so off axis it didn't get picked up. If it didn't get picked up, well, that's too bad. Anyway, top level learning. Again, we have the idea that from the bottom level, if a particular activation can lead to the extraction of a rule, it will do so and go from bottom level to top level. This is going to then be subjected to further refinement, possibly, depending on whether a rule invariably succeeds or we discover exceptions to it. More on that in a little bit. Then, of course, you can basically create other rules, essentially stochastically or randomly, or have some pool of potential rules that can be drawn from, and this can guide the agent behavior. Essentially things to try, if you will. Whether they succeed or not can only be discovered upon actually activating it. IRL is a kind of a specialized mechanism. Then fixed rules are just simply basically rules that are essentially baked in. They're going to be rules that automatically cover things that you know the agent needs to be able to do. You get this input state, and then of course it leads to that action. That's it. Just put it in as a fixed rule. This is essentially a way of shortcutting things that might otherwise be very difficult and lengthy to implement where you don't really need it here. Now, rule instruction and refinement is kind of interesting because this is a way of actually getting quite a bit of the expressive power of ACS working for you here. If the action at the bottom level is successful, then this can lead to the construction of a rule that shows up at the top level. In subsequent interactions, as the slide says here, the rule is refined by considering the outcomes by applying the rule. Now, supposing, for example, some rule requires that you have a small red square on screen, and it was successful, and then another application says, I had a small yellow square on screen, and that was successful. And then I get a small blue square on screen, and the action was successful. Now, it might say, gee, if I maybe try small green square on screen, I can now say I have all four of those dimensions are all good. They all actually succeed, and I can now disregard color altogether. So I can generalize the rule and say color is not any longer important. Now, if at some subsequent activation I discover that, gee, the small yellow square doesn't always lead to success, I'm forced to abandon my generalized rule and go back to saying, if it was red, green, or blue, you were okay, but if it was yellow, you're not necessarily okay. Through a process that Clarion is doing continuously, rules become more specialized, meaning we add more particular dimension values to the rule, which means you need this to be true also for the rule to be true. So if I say I noticed that I had success with red, green, and blue small squares, then I can put that rule in my set. And of course, if I discover that the blue didn't always work either, I can then delete the small blue square from my collection of rules. Through a process like this, rules can become more specific or more general. General rules have fewer dimension value pairs in the condition side of the rule, because you're saying that whenever something isn't included in that, it's a don't care state. You basically don't care what that is in the world. You get the rule match, and therefore you get the recommended action from that. On the other hand, more specific rules require more fine-grained indications. Well, you can use this, this, and this, but not that or that, or you need this and this to be present. So rules like that get more specific as you discover that sometimes certain dimension value pairs invariably lead to success, others may not necessarily lead to success, so you back off from rules that don't work and generalize when a rule can be found to be always working across a range of possible values. Does that make sense how I'm putting that? I don't know if that is completely clear. The notion being that, again, more general rules require fewer matched dimension value pairs because the rule is more applicable in more situations. A more specific rule has to basically list which of those conditions really need to be there for that rule to be good. And this is a process that operates automatically in Clarion. You create your neural nets at the bottom level, and the rules will find their way into the top level without your doing anything in particular in the code. So you basically get this always running. And it's actually, I'd say, one of the more powerful features Clarion actually offers. Yes?
Can rules be extracted from failures of the neural network that fail to do something to make rule
restore the rule, it basically deletes from that rule what that condition was that didn't lead to success. So for example, to go back to the small colored square example, if I had red, green, and blue as three rules, there's basically three rules there, and the blue one stopped working for me, then I delete that rule effectively. So I just have the red and the green one surviving. Rules are basically dropped when when they don't work, but they're not completely forgotten. To go to a kind of a point with the colors again, if I discover that red, yellow, and blue were all good for small squares, and then I find that, you know, green was also good, now all four possible values of the color dimension have been accounted for. That can go away entirely. But if later on I discover I have to get more specific again, what occurs in the code, if you haven't changed it, Nick, is that we hold on to those previous more specific rules and put the more general rule in its place. And if we then have to abandon the general rule, we restore the ones that were previously in there and more specific. So this is basically sort of an ongoing way of monitoring how the rules actually can get more and less specific over time. It's a very powerful capability. It's one that I don't really explore the full ramifications of in some of our simulation models. But that's basically how RER works, and it's really one of the most important things in here. So I kind of beat this to death already. This is essentially what's going on. You look at the state of the DB pairs and so forth. There are other things doing in here I'm not going to dwell on either, because I guess we're already running out of time or running late. Positive and negative match criteria can also be established here to, again, refine it. Generalization, again, we've been talking about this right along, taking more specific rules and then finding the commonality and extracting that out so that I can arrive at a more general rule without necessarily forgetting what those specific antecedents were. If I later have to abandon the general rule, I restore those antecedents that previously worked for me. On the other hand, specialization, I have a general rule, but then discover some of those DB pairs in fact don't work. I now have to abandon what that commonality was and drill out or extract out more specific sub-rules, which are going to be how you guide the behavior that way. So this is how that all works. So one example is this task here. I remember the name of it. It's the sequential relations task, and essentially from Kern and Keel. And what you're doing is giving the subject a series of numbers. I'll go ahead to where that is here. So you're presented with a sequence of numbers, and you're trying to discern or determine what rules are that guide how numbers can arrive in a sequence of digits. So I'm presenting, for example, 1, 2, 3, 2, 3, and following it with a 4, and I see the number of occasions of this. I may want to say, gee, if ever I see 1, 2, 3, 2, 3, it's always followed by a 4. Now, there's never any exception to that. That rule will find its way to the top level. Now, supposing there are other things which lead to a 4. Maybe I have 3, 2, 3, 2, 3, or 4, 2, 3, 2, 3, or 2, 2, 3, 2, 3. This leads to that next generalization where the first position is a don't care. I now know that 1 or 2 or 3 or 4, when followed by 2, 3, 2, 3, invariably leads to a 4. And the asterisk here means the don't care state. So what I'm doing here is that first digit position is now not needed to be looked at anymore in determining what the sequence is. Maybe after more exposure to sequences of numbers, I determine that as long as I have something, and then a 2, and then something, and then a 2, 3, that always leads to a 4. This rule is a little bit more general than the one prior, because again, I have more don't care states. Here I'm only needing to get 3 digits in a particular position to lead to a 4. In the previous one, I needed 4 digits to lead to that 4. So this is going to be how it works. You can present streams of these digits to the agent and have it discern rules from that. And then, of course, in a human task, you can see how well they get and see if they can do that. And we can model a similar behavior inside of Clarion. Any questions so far about how that operates? It's kind of a capsule view of it, but I just looked over several slides. Should I go back to those slides, or don't you care?
No, I just have a question. So I guess how general do the rules end up being? So are they specific to a particular task, or can you take a set of rules and then apply it to a similar task, maybe some nuances, but a similar structure?
That's actually a two-part question, an interesting question. The first part is that the rules become as general or as specific as the environment and the behavior of the agent in the world has been. In other words, if in fact rules needed a lot of specialization where there were particular exceptional cases that might lead to a rule working most of the time, but there are times when it doesn't work, then you'll start seeing a lot of specific rules emerging that cover the fact that a simpler rule didn't cover it. On the other hand, if you can find rules that are really more global in scope, that operate over a variety of circumstances, and the rules don't fail to work when you do that, then you'll see fewer and more generalized rules emerging. It really is entirely dependent on the environment you place the agent in and what it discovers in operating in the world as it proceeds. So you can't say in advance whether you're going to get mostly general or mostly specific. It'll be as general or specific as the discovery process, if you will, the agent goes through yields.
One limitation though is that it can't be, it can't generalize all the way up to a match all rule.
That's true.
If it gets to the point where every dimension is don't care, then the rule's discarded, or it's left in the second most generalized state. Because if it's going to match everything, then it's equally as unuseful as, let's say, if it was matching nothing, right?
Yeah, that's some of the end conditions there. If that were the case, you'd probably have to look at how you model the problem. You'd probably have something broken in your modeling assumptions, I would say. And what was your second question again? I didn't.
Oh, I mean, it was kind of an answer. I mean, can rules that are learned be applied to a
mapping
different,
completely unrelated.
not necessarily unrelated,
Yeah.
but in the sense that you find in psychology experiments that certain sensory input will prime people for other types of responses. And I'm wondering, did you see any of that where a rule will carry over to a different task, or is that not included in this system at this point?
It depends on how you set it up.
Yeah, you probably need to include like both domains in the overarching model, and then see if you get that migration happening. But that would be a matter of how you approach the simulation. I don't think you can say, gee, here's a bunch of rules from this domain having to do with music. We plug it into cooking. Wouldn't work. I mean, that would not be realistic.
It would work. It works to the extent that two different domains have overlapping features. If I have a set of rules for one domain, which are activated by certain features within that domain, and I transfer that over to a different domain, as long as that other domain has those same features, then there's no reason why you couldn't set up those rules to fire. Now you would probably need to have other constraints to those rules, such as allowing them to match partially, right, in order to be activated, or you make sure that they are generalized enough so that they'll actually be selected within that other domain. But as long as there's overlapping features, yeah, those rules could also be activated to a certain extent within another domain.
Okay. Okay, any other questions? Okay. Independent rule learning is a variation of RER. Essentially, you don't really use the bottom level. You simply have rules that can either be generated randomly by the way you set up your model, or possibly something that is specific to the domain you're working in. You know those rules need to be in place anyway. And then from there, again, they go through and get tested against the real world with an information gain metric. And again, if you cannot get the rules to stabilize, you may drop it because it's information gain below a threshold. Not going to get too much into IRLs here. And fixed rules sort of replicate the notion of essentially baked-in knowledge, things that you know will always be in there. And this is just a way of basically shortcutting or simplifying what you want. Again,
not exactly baked in.
Not baked in.
It represents one-shot learning. This idea that somebody gives you a piece of knowledge, explains a piece of knowledge to you, and it's there. You have it. You get the rule, and then you can subsequently apply it. All right. So it's the idea that of either instruction or one-shot learning.
Okay. Any questions about? Not much to say about those at this juncture here. Level integration. Of course, this is now getting to the issue of how do you deal with the contention between the top level and the bottom level here. There is a notion of selecting randomly or stochastically between the two based on parameter values that can be set in your model or altered later by the MCS's operation, and also ways of doing combination here. In this little discussion here, I would assume that there's one bottom level network and one body of top level rules associated with that network here. You can, of course, have multiples if you wish. Yes?
Is there a difference between the terms random and stochastic?
I think they're basically stochastic is a fancy way of saying random. In the jargon here, we mean stochastic to mean basically a Boltzmann distribution behavior, but stochastic is often taken to mean synonymously with random. I don't know if you.
Well, it's not random, it's
Yeah, there's random within very
probabilistic.
strict restraints. Yeah,
So-
it's within constraints that are determined by what you're selecting from. It's not
Right,
free.
right, you're not, I mean, I guess in the case that you're doing a stochastic selection where you have a incredibly high amount of temperature, a high amount of noise, or you have, actions which all have the same probability. Okay, and we're talking about probability, we're talking about probability of success. In that particular case, then yes, yeah, it's basically a flip of a coin, right? But what we're usually talking about here is we're talking about 5 or 6 different actions which all have different likelihoods of being successful in a given context, and that what stochastic selection does is it does a probabilistic selection of them, which means that the most likely answer is usually going to be the one that's selected, but it's not a guarantee.
Where you're taking into account that lesser weighted action recommendations could be picked too. You're not doing a winner take all. That's what we mean here.
It's also Clarion, and this is a tenet of Clarion, that Clarion assumes that human action is not purely deterministic, that there is a certain amount of variability to human action, a certain amount of stochasticity. Now, the amount of stochasticity fluctuates based on, you know, your domain confidence or your experience, but that when it comes down to it, there are times where people perform actions that are, for all intents and purposes, somewhat random, or at least to a certain extent. At a certain level, there's a randomness to it.
And this has to do with a temperature parameter in the Boltzmann distribution that helps you decide that. No need to get into that, but basically, of course, at the top level, there is a probability of selecting a rule from one of these 3 collections or rule systems, the RAR rule set, IRL rule set, and the fixed rule set. Now, whatever's left over, the residue of that is the probability of going with the bottom level action recommendation. And again, we use the idea of a Boltzmann distribution to make that decision. These are things that can also be fixed at design time when you build your model, or be allowed to change over time by a module in the MCS. That can be something which is not frozen in time, but can be dynamically changed here. And this is basically how you do it. If you want to force absolutely deterministic thing, essentially winner take all kind of a thing, then you can make it do that too if you wish. The combination one is basically also dealing with the possibility that, you know, maybe the top down should be the top level should be the one that determines, or the bottom level is the one that needs to be determined. And the 2 terms for that here are top down guidance or bottom up rectification. And this is basically a determination of which layer is believed to have, or which level is believed to have the better answer. That's not really saying it accurately, it's kind of that notion here. So in bottom up rectification, the bottom level thing sends its recommendations to the top level, and of course, the top level may have a better notion of what it needs to do, if you will, by the rule set it has, and this can then be used to you know, change what the bottom level decides. Top level is the one deciding, it's being pushed down to the bottom level and basically causing the bottom level to be subjected to a learning cycle, if you will. So that, for example, what happens is that, you know, if you have a rule in the top level that is known good, you can basically overrule the bottom level, and in so doing, cause the bottom level to slightly move toward what the bottom level is dictating here. And then just before, the slide I had before again, observe the current state at the bottom level, produce activations of the output nodes that suggest actions, and then perhaps choose stochastically from one of those. In parallel with that, look at the top level, see which rules have activated, and then perhaps select one rule from them stochastically. And then with those 2 in hand, you then stochastically decide between top and bottom level overall, perform the action in the world, see what it does, and then use that to guide reinforcement learning and so forth, update the bottom level with that, and possibly also alter the rules of the top level, again in parallel, and then go back to the top and repeat it. So there's this notion that there's this parallelism of top level and bottom level processing with this communication between the levels taking place, and that is basically what the Any questions about that? Yes.
So when you first introduced this in the intro, you said that the procedural knowledge that's you could think of as the high-level ACS using a rule-based knowledge tends to be slower but more precise than the implicit knowledge used by the bottom level. Is that an artifact of just it being a computer architecture and it just takes longer to run through those rule-based situations?
That's what we see, and that's what we see in human behavior. I mean, neural nets are basically, of course, in software we have to use a serialized way of representing how a neural net gets computed. But of course, with real neurons, we're all operating in a massively parallel way. So the answer kicks out of a neural net quickly. The top level is really your cognition applied to an issue. So you're applying a process that really does run a lot more slowly. The implementation issues having to do with how many CPUs we can devote to something, for example, we're dealing with binomial architecture computers. So we have to chunk through all that math to create a neural net behavior. In a real brain, that all happens in parallel. So the answer is not instantaneous, but really quick. On the other hand, the top level thing, which is rule-based, is a matter of like, well, what rules do I know and what do I apply? I need to reason over it. So that's a slower process. I mean,
so I guess what I was thinking of is when you're talking about learning from a human standpoint, you have a transition from moving from a novice performer on some task to an expert performer on some task. That is sometimes talked about as moving from using declarative knowledge about the task, where you're going through specific steps, to procedural knowledge, where you're just using a basically condition response type of rule set. And that procedural knowledge stage where you have an expert performer is typified as being faster and more fluid and more continuous than the declarative stage that a novice would use. So is this not then the same thinking of declarative knowledge versus procedural knowledge? Is this based
well,
on
I don't know about declarative versus procedural. I mean, you have procedural knowledge which is expressed symbolically. Like I want to learn how to play a C major scale. I follow C with D and then with E and then with F and so forth. But I can talk my way through it. Now, if I'm a beginner at the piano, I'm going to be verbalizing, if you will, and that's really a rule-based approach to how I play a C major scale. After I practice it for a while, I can shed the reasoning over it, if you will, and just know how to sequence those notes.
Right.
So it becomes more impressed onto whatever neurons are dealing with the motor system that makes you play a C major scale, and it becomes fluid and precise and automatic, if you will. You don't need to reason over it anymore, and you can speed the process up. You'll be able to do it. But if you're learning something new, you do go through that beginning, if you will, with rule notions like I need to do this now or I need to do this now, and then over time they become routinized and you don't need to really think about them anymore. So you do move to fluid and more accurate behavior. So I guess maybe the initial point of your question, like, is it more precise to be at a rule level? Well, it may be if the rule can be so expressed, but for the motor things that make like playing at scale happen, what does precise mean except to play it really accurately? But that comes with training at the motor level, and that's going to be better if you don't verbalize or don't reason over it. That's going to result in clunky, awkward performance. And any music instructor will tell you the first thing you want to do is get past verbalizing what you're playing. You know, so that's part of any skilled performance that you want to get to that point. So that's both mechanisms are in place at Clarion. So if you wanted to simulate that kind of problem space, you could do so. You know.
Basically, what he's explaining here is the method of top-down learning. Okay, the idea being that the bottom level is less accurate, but it's quicker. Top level is this kind of slow procedural reasoning type of activities, and that over time, what happens is that when you're moving slower and going step by step through everything, that over time, those kind of step by step processes, which are accurate when they're slow, get proceduralized into the bottom level. Now, once it's been automated into the bottom level can take over and do these same kind of actions at a much more rapid pace without error once it's been trained. Now, but before error, if you try to speed it up, all of a sudden the bottom level is trying to react, and it doesn't have proper training to this, and it's going to make mistakes.
Okay, yeah, I guess that's what I was wondering. So the top level rules can be proceduralized down to the bottom level to to train those
Yes.
networks to
That's
have very fast, accurate
Top down,
performance.
that's
Oh, that's
the
the
top-down
top-down
learning.
mechanism that we have.
Right.
Top-down learning.
Okay, working memory. Of course, this is also a well-established idea, although there's been some contention about that. The notion of a short-term memory or a limited capacity memory system here. And this is essentially an area that is in the ACS to store this information here. Information in the working memory does fade over time relatively quickly, and new items coming into working memory can drive out older, less heavily activated items as well. It is limited, and there are multiple stores. We have different ones for different subsystems, as we're going to see. In particular, these three here. You can have a working memory buffer, if you will, for visual spatial information, one for the auditory, and then if you need other working memory systems within it, you can add them yourself. But the notion is that we do have a notion of a working memory for things seen and a working memory for things heard, and maybe a working memory for things we're doing cognitions about. So these are things where you can provide this any way you want within the Clarion system. But the notion is that you do have a capacity limitation in the working memory area. And one of the things the ACS does is have a set of working memory actions which allow you to manage the operation of working memory. If something has been dealt with and is now satisfied, you can cause a command to be issued in the ACS, which causes that working memory element to basically be deleted, and thereby opening up another slot here. So the working memory actions I just kind of said here, you can add items to working memory, you can remove items to working memory, and this is essentially what you can do here. You can clear the whole thing out, or you can choose to do nothing. And of course, the base level activation technique is used to decide the aging of memory elements in working memory. Elements that have not been activated in a while eventually drop away. This is also a buffer system, if you will, between the ACS and the NACS. The ACS can post to working memory, request to the NACS, and results coming back from the NACS arrive in working memory too. So if you think of a word association problem, for example, you hear a word, you say, okay, please do retrievals of words similar to this, and then the NACS will go dutifully search its knowledge store and then possibly produce quite a long list of these. And these would then appear as a working memory element of a collection of matched words or nearby words. And that could be a thing you can make happen there as well. Again, I'm glossing over a lot of detail, but Clarion does have the notion of a limited capacity working memory component within the ACS subsystem or ACS. Any questions about working memory? Didn't say too much about it, but any questions? Okay. Okay, simulation examples. To get to the serial reaction time task again by Kern and Keel. We looked at this a little bit before. Here are some performance results we got out of here, and we were able to find a pretty good fit, basically. This was done with a simplified Q-learning backpropagation network, where the learning happens at the bottom level. We're basically impressing onto the input nodes the number of sequences we're seeing, and then allowing the bottom to top level migration of rule extractions happening there. And I think the model here we had with three groups of subjects here. We have people who use the higher level rule, they're less aware of what's going on, and so forth. And this was confirmed. So there's things here. I think we have more details about this in one of the papers, right? I'm trying to remember where this was found. Letter counting task. I don't think I need to go through the simulation examples too much here. Again, we find in general we can get a good fit with this as well. And these are, again, relatively simple models involving only the ACS. We have simply a single neural net with so many input, hidden, and output nodes in it, and then we allow RER to do its thing to go from there. Again, what happens here. I don't think we need to go through this too much. I thought I hit all these slides. I guess I didn't. I wasn't going to show this many slides and so forth. I think I'm really issue with that. Let's just go past all this. I don't think we need to worry about that too much.
Are any of those models actually available online as well, or it's actually?
A lot of these models date to back when Clarion was the Java implementation. I don't think that many have been ported, so at the moment, no.
Many of them date back to even possibly before that.
Yeah, some of these were more
yeah.
handcrafted, if you will.
Yes.
Yeah.
So a lot of them haven't been ported over. And we run into problems like for the minefield task that
Yeah.
was shown very briefly here. That used the specialized front end, which was developed by one of the military, wings, or somebody working within it, and we no longer have access to that front end. So we couldn't really recreate that task.
One interesting one, if you kind of care about that, is one that Mark Stefano used in his doctoral work, where they used a game called Space Fortress, which is actually used by Israeli military to train people. And Space Fortress is actually a very complex cognitive task. And the point of it, and Mark did this in Act R, was to have it learn how to play Space Fortress accurately, where you're both moving around to evade being fired upon while simultaneously firing at a target. And while that's going on, you're also monitoring quite a bit of data that's basically on readout display. Mark was successfully able to get the system to train to play Space Fortress with considerable accuracy. We've had it as a task we would like to pursue one of these days to actually replicate that with Clarion, and that would be kind of analogous to the minefield task. Again, we don't have access to this anymore. One candidate we could do this with would be Space Fortress. That would be a terrific thing to try to build a simulation model for, if somebody wants to take that on. So, anyway, you had your hand up?
I was just thinking about some of the games I've worked on, and sort of which one of which had quite a live universe.
Okay.
It was a full production game, and I was just thinking, as I've been listening to you talk and reading the slides, it's sort of been tickling at the back of my mind, trying to do that sort of thing, and how you would set that up with Clarion. Even just quite a simple, basic thing. You set up multiple agents to start running.
Well, it's not exactly a trivial process. I know this is Mark's doctoral dissertation, so it was not a small project by any means to build that. What's nice about it, he did successfully get ACT-R to learn Space Fortress in a way that really worked. And his implementation was actually better than the one that came out of Carnegie Mellon. The Carnegie Mellon one, we believe, did some cheating, whereas Mark's was not that way. So yes, in principle, you could build an agent that is competent to play a given kind of task like this. Minefield task is probably out of reach for us, as Nick pointed out, but Space Fortress is one that is within reach. We can get at that material and possibly build an agent for it.
In terms of interacting with front ends, the agent and the world that the front end world of the agent is in can be somewhat separated. I mean, at least to the point that you figure out how the visual world that we see, how you can translate that into some sort of featurized representation, and then the featurized representation can be handed into the agent, and the agent will see it can see this visual world in its own kind of language. And we've done this in a bunch of different front ends. Dan Vexler over at AFRL has done a lot of work integrating cognitive models with a Second Life front end. And so we did some work a while back, seeing if we could hook Clarion up to that portal into Second Life, and sure enough, we were able to do it to a certain extent. We've also worked on integrating Clarion with robots using the robotics lab here, and allowing the robots themselves to featurize what it is it's seeing, and then having the Clarion agents do the decision making based off of that. But I mean, by the time it gets into Clarion, it can be fairly featurized, so that the agent can actually make useful action recommendations based off of
And I would add to
arbitrary
that,
front ends.
and I would add to that the process of setting up that featurization mapping is one you've got to give close consideration to, because if you are haphazard with that, you're not going to likely get the system to converge on behavior you'll find effective. So feature featurization is part of the problem. I know that in Mark's case, that was a big issue, was how exactly do you want to model the world and at what level of granularity.
Yeah, I mean, to be honest, my thought was not so much have you played a game, but actually, given the nature that it was a simulate, the games that I'm thinking about was a simulated universe, sort of put agents in, have set up different agents with different personalities, all running Clarions, and put it into the system and let it go. I mean, and I was thinking of the game Elite. I mean, if you took away the front end and just gave the Clarion system the raw data that Elite had, which is comparatively simple if you think about it, and say, okay, here's the system, go do something with it. I mean, Elite's a fascinating game. It's so completely open-ended. There are as many games of Elite as there are people who used to play it.
Certainly, and this is an interesting point because, you know, obviously we expect the agent to get more competent playing. You know, winning the game is the objective, that's the goal of the agent. So you want to do that. We're getting a little far afield here, but these are good points, and right now we haven't really gotten deeply into the idea of let's have Clarion be a competent game player in some context. If I were to pick one right now, I would say Space Fortress, only because it is an attempt to replicate other projects that have used Space Fortress. It's become kind of a favorite game example in Cox side work because A, it's available, B, you can find comparative data for it. But you're right, in principle, if you can get your featurization correct, you could presumably get agents that will, through the process of learning neural net behaviors and discovering rules, get better and better at playing the game.
But I mean, we have done several examples, I think, of these types of tasks where we've extracted out the essentials of a front end. So without actually creating a front end on its own, we've extracted out the essentials of the front end and had agents perform tasks without that. So for example, you know, we had a couple of students last semester do Towers of Hanoi, right? And they were able to do the Towers of Hanoi without actually creating Towers of Hanoi front end for the agent to interact with. Or, you know, last year we had somebody do the air traffic control task, which involves a really complicated kind of front end that, at least for a long time, the Air Force used to give to their, you know, to their pilot or to their air traffic controllers to kind of, you know, do some very simple early on training. And he was able to capture the essentials of that particular task and actually published his findings.
Who was that name?
That was, now it's being recorded, me forgetting his name.
I don't recall. I hadn't seen that. That's interesting that we've got it that way. And the air traffic control is sort of in that space roughly, yeah.
And I know we have to move on, but just one small thing. I mean, I know Clarion is very much described as a psychological simulation tool. And one reason why I'm so fond of Elite is because when you talk about games, you talk about winning the game. Elite had no win conditions. It was entirely open-ended. So if you were to set up something to play a Clarion agent that was capable of playing Elite, how would it know when it had won? Like, if I used to sit down and play Elite, I could say, okay, well, I'm going to kill so many pirates, I'm going to make so much money, I'm going to visit every star system. You know. So there are various possible win conditions, but I can meet those and I can keep playing. You know, from sort of psychological
Well,
perspective.
if you step back from the thing, maybe one level removed from that, then of course your goals, the goals you design into the agent are those win conditions you specify. But if you want to keep playing after that, you have additional goals to say, you know, satisfy curiosity or alleviation of boredom or some goals like that, which is why you keep playing after you quote won. Again, if that is the nature of the problem that you're trying to model, you would need to be thinking in those terms in terms of how you would set up a goal structure, for instance. If it's just a matter of getting to the win state, then upon reaching the win state, game over. But if it's not that way, we keep going, then there's other goals operating besides the win state goal. And you would simply have to model that in order to get that original behavior you're trying to do. So that seems how you approach it. Again, this is again an issue of like going from the world you're trying to model to featurization of that and all the rest of that is not a trivial process. It's true for anyone working in any cognitive architecture, that you have to deal with those questions. So it'd be a great example to try, especially in a multi-agent simulation. And oh, by the way, yes, you can set up multi-agent simulations of Clarion. You can have several agents all operating in parallel simultaneously effectively, each operating according to a different set of goals, and then see what happens when they bump into each other. That is a perfectly reasonable emulation to set up in Clarion, so you could do that if you wish. And then from that, you can see those behaviors.
By the
Anyway,
way,
we might need to move on. We're kind of pressed for time.
but
here,
by
that's
the
all
way,
right.
the air traffic control task was James Brooks who did it. And
Okay.
actually, you can find that paper
Pick it up.
from the Brains Mind Institute ICBM 2012 proceedings. So Brain Mind Institute conference.
That's Brooks, you said, is?
Yeah, James
okay.
Brooks.
Okay.
And I'm second author, Wilson and Son third author. So
Okay, so there are some more recent examples that we have with the current implementation. So just to summarize some of this stuff here, the bottom level is implemented as backpropagation networks, and Q-learning, simplified Q-learning, and so forth are available at the bottom level. The top level is a collection of rules with condition chunk nodes leading to, condition chunks leading to action chunks based on, again, rule matching. And then from that, we have the rule extraction refinement mechanism that allows rules to become more general or more specific, independent rule learning for trial rules, and of course the one-shot learning kind of idea, or built-in rules idea from fixed rules. So that's what occurs there. We make our decisions among action recommendations stochastically to whatever temperature in the Boltzmann distribution you want. You can make it be absolutely deterministic if you so wish. And we also have the process of whether the top will guide the bottom towards how the decision is arrived at, or where the bottom guides the top and how the decision is arrived at. These are things you can model. Working memory is part of the ACS environment. It is a limited capacity memory system, and there can be several elements in the working memory do fade over time according to base level activation. And working memory actions are things the ACS can do with the contents of working memory as well. It's also a buffer area, if you will, between the ACS and the NACS, where the NACS is performing retrievals and reasoning in the service of NACS request. So that's basically the ACS. That's probably the longest module of the day because it is the most important single module, if you want to look at it that way. They're all the modules are important, but the ACS is the fundamental one. You can build an agent with nothing more than an ACS. Every Clarion agent needs at least this. And of course, other pieces are going to be, as you get your models more sophisticated. So any closing questions for the ACS?